Hi, this is the start of my video on the great surveys of the 18th century. And I've started by bringing out my theodolite, which we'll talk about here in a second. The great surveys of the 18th century were all over the world, but the one we're going to look at is the Lapland survey, which the new hat and the snow will be very helpful for. Now, the Great Survey was done with some by these standards, very primitive instruments. This was the best theodolite of the, I'd say, 20th century. The U.S. Army attempted to make one of these during World War II because they're imported from Switzerland. They let two large contracts to Gurley and Köfel and Esser to do that and were unsuccessful. It has glass graduations. Down here, one for horizontal, and up here, one for vertical. It has a micrometer right here. You have a telescope eyepiece and a microscope eyepiece. The microscope moves down through. And this was really an excellent instrument, wonderful level, and so on. Theodolites of the 18th century, quadrants and theodolites, were not tremendously accurate. They had a number of errors, and you had to take measurements from all sorts of different positions to get any kind of reliability out of it. One of the things that this theodolite and the 19th century theodolites had, or transiting instruments, was the ability to transit the telescope. By that I mean swing it clear around. So I take a reading this way, and then once I get it, I lock it. Then I take my reading over here. Then I transit the telescope like this, unlock, and swing it around 180 degrees, and take the reading again. And what this gives me is the errors in the instrument that would go one direction are canceled when I transit the telescope the other way. Likewise on the vertical, I can take a reading on the vertical, moving it up and down until I find what I'm looking for. Then record that reading, go 180 degrees, transit the telescope, and read again. And what we get is canceling of the vertical errors that might exist. This telescope, the theodolites of the 18th century were mostly accurate within perhaps 4 or 5 seconds. Some of them got down by the end of the 18th century to 1 or 2 seconds of arc. Some of the astronomical instruments were good down to 1/10 of a second or so. This one is given an accuracy of 1/2 second of arc, 1 second of arc, and it's readable to 1 second of arc with care, with the turning of the micrometer. So that's the start. Now I do have a few other instruments I want to show you because they'll kind of make some of this clearer. The basic principle, of course, is you have levels which mostly the 18th century used plumb lines. You have a telescope, and you have some sort of microscope to read the graduations. Now you'll probably see a great many more of these than you will of the others. This is a sometimes known as a builder's level, and it's much simpler. It has leveling screws at the bottom, and you get the bubble lined up here. It's got just the one little level, but it has a little thing here for turning. You can read degrees here. It will, so you can actually measure horizontal angles with it. But it has, and here's the focus. The main strength is it has a prism inside, which maintains level. The prism is on a little pendulum, so that no matter how this is moved up and down, or as it comes around, you always read a level point. It's called an automatic level. And they're, for most building projects, of course now they're totally replaced by the laser levels, but for most building projects this is probably the most useful tool, because you mostly want to know where the level plane is. As you spin this around, every site you take is on the level plane. This is a somewhat more primitive transit, early 20th century. You can notice it has a microscope here for the vertical, to read the vertical graduations, which are back behind that. It has a microscope here for reading the horizontal graduations, and it has another one over here so that you can read the graduations twice from both opposite sides, and thereby get some improved accuracy. It has levels on the bottom plate. It has a level on the telescope, and it has a level up here. I wanted to come out here and give a little demonstration of, I guess, surveying techniques. I'm going to use this, which is my Brunton Pocket Transit, to give some ideas. You open it up to begin with. You have all sorts of options for sighting. This is probably the most accurate. You turn this down, and then you can sight like this and read the compass needle while you're sighting. And then you turn to another point and you can read the new angle. That's probably the way it's most often used. For vertical reading, you have the vertical controller here that alters the angle, and you do the same thing. You can just put this like this and sight through the target and move this until you see the bubble go level, which is right there. Then you can read the value right there. You could do a number of other things with this, laying it out like this on a flat platform. You could sight this way and draw lines to do what's called plane tabling, creating a map. Two expeditions were sent by the king and the French Academy of Science to determine the shape of the Earth. Because the Earth rotates, it is to be expected that the centripetal force will cause a slight bulge at the equator. The Lapland and Peru surveys were to check this by measuring the length of a degree of latitude. If the lengths were the same, the Earth would be a perfect sphere. If the Earth were a perfect sphere, Newton, Huygens, and all the physics were wrong somehow. In any event, knowing the precise shape would be an aid to ship navigation, since measuring angles is used to determine distance at sea. This is a small sextant, so called because it's 1/6 of a circle, and it's used mostly for ship navigation. It will measure from 0 to 120 degrees. On this graduation here, the small telescope just goes through this mirror, half mirror here. And the way it works is very simple. If you look here, you will see the light entering here will be reflected here and then into the telescope, so that at 0 degrees down here, the image through the glass and the image through the mirror are the same. As you move it, say over here, the image comes down at a higher angle. So it allows very precise measurement. The advantage of a sextant for seaborne navigation is that as the ship moves up and down, the image of the horizon seen through the glass and the image seen through the reflection will be the same, so that none of the motion is detectable. They're not particularly useful on land, however, because we don't have the level horizon. You need a bubble or a plumb bob to establish that. On aircraft, they also had a bubble sextant, where instead of having an image of the horizon, you would have an image of a bubble of a level that you were measuring against. Quite an accurate, very simple device. This is a very small version, almost a toy. Possibly might be called a boat sextant, or I think this one was probably made for the Boy Scouts. But it has a very nice graduation, and these filters, by the way, coming around this way, interrupt the light and make it possible to sight the sun. The nautical mile is set to the length of 1 minute of average latitude. This means 60 nautical miles are 1 degree. This gives rise to some salty poetry. 60 nautical miles for 1 degree as you sail off a lee. Or, I know there's salt in the sea, I know the taste of tea, I know 60 miles per degree. Or my own favorite about the radius of the Earth. The radius is 60 nautical miles for 1 degree times 57.3. Back to Lapland. The idea is simple. Measure a north-south length, getting the latitude at each end. Divide the length by the latitude difference to get the distance per degree. The work was not easy, especially in frozen Lapland. Since measuring distances is hard and measuring angles is easy, only one baseline distance need be measured. All the rest is done with angles. Given the angles and one distance, the law of sines gives the other distances. The work began in July of 1736 at the town of Tornea, now Torneo, near the mouth of the river. The expedition sailed upriver to place the baseline near the center of the survey. 2 signals made of poles were set up to form the baseline. There was no need to waste time measuring the baseline at the beginning, because they had to measure the all-important angles while weather was good. The baseline would be measured later after snow fell and the river froze. The signals were set up on hilltops where they might be observed from the baseline or from each other. Angles were measured from every signal to the others as many ways as possible. Crude observatories were set up at each end of the measurements, and the change of latitude of a star was measured. When winter set in, rods were prepared from the length standard to measure the baseline. The line was measured by 2 independent crews working end over end through the snow. The error in measurement was less than a foot. Calculations were done during the dark of winter. The trip back to France the next year wasn't easy, with a shipwreck and everything. To measure the angles, they had quadrants equipped with telescopes and screw micrometers. Quadrants at this time could be nearly as accurate as some modern theodolites. An error of less than 10 seconds of arc was possible with a careful operator. To measure the baseline, they made wooden rods referenced to a standard toise they brought from Paris. 2 such standards had been made, one for Lapland and one for Peru. The Lapland standard was lost in a shipwreck, but the Peru toise became the national standard length, called first the Toise de Peru and later the Toise de l'Académie. To measure the latitude, they had a zenith sector made by George Graham. To examine the zenith sector in some detail, I've made a little model. In order to demonstrate how a sector would work, the Graham sector, you had this is a little model with the most important elements. It has a telescope pointing vertically toward the zenith with a plumb bob and a string past a graduated little scale. And by moving this to a star, focusing it on the star, you can read the angle from the plumb bob. The rest, a frame to level things up and so on, is also, of course, part of the picture. This was the sector used at Lapland. In the Lapland survey, the sectors after this had the ability to rotate the telescope 180 degrees, which this one doesn't have, allowing you to cancel the error that might exist in the readings, because you could get the reading on one side, then turn it around and get the reading on the other side and average them. The advantage of the zenith sector, I got a little model here, is that it's aimed straight up, which means that atmospheric refraction is minimized or eliminated altogether. And also that there's a simple way of determining the latitude. Here's a sphere which has the stars. It's a globe, but it has the stars instead of the map of the Earth. And the idea is very simple. The longitude of a place on the Earth is related to what's known as the right ascension, which is the angle around this way. All of these here on this have the same right ascension, and they also have the same longitude at midnight in the sky. The declination, what astronomers call the declination, goes this way, is the latitude. So if I want to get the latitude of a place, all I have to do is know the latitude of the star in question, and this, by the way, is the star they used for the Lapland survey. The Peruvian survey would have used something more down lower, possibly Sirius or Betelgeuse, something like that. And you can measure straight up with a zenith telescope or a zenith sector and obtain a very precise measurement of the latitude or longitude with a star chart, with a catalog of stars that gives you the declination and right ascension of the stars. This makes celestial navigation possible. The Peru survey was done the same way over 3 degrees of arc. It took 10 years for the results to get back to France. The trip was much harder, and the 3 scientists did not altogether agree on things. The 2 surveys demonstrated the flattening at the poles with accuracy of 1 or 2% of current values. Mason-Dixon. In 1763, Mason and Dixon went to America with the finest equipment possible to survey the border between Pennsylvania and Maryland. They established the accurate latitude of an observatory in Philadelphia, then surveyed south to a starting point and headed west. Schehallion. The Mason and Dixon survey found some errors between their line and the measured latitude at certain points, and hypothesized that mountains were attracting the plumb bobs on the zenith sector. When Charles Mason returned to the Greenwich Observatory, he was asked to find a mountain where this might be tested. He decided on Schehallion, a mountain near the center of Scotland. The idea was again simple. Set up observatories on the north and south sides of a mountain, measure the latitude of stars at each, make a correction for the carefully surveyed distance between the observatories. Remember, 60 nautical miles in 1 degree of latitude. Any error after the distance correction would be the pull of the mountain. The ratio between the sides of the triangle would be the same as the ratios of the mass of the mountain to the mass of the Earth. Measuring some 100 stars and averaging, Neville Maskelyne found an error of about 11 seconds of arc. The mountain was surveyed and rock densities taken. Charles Hutton was hired to study the results and calculate an estimate of the mountain's mass, and therefore the Earth's mass. Graduating instruments. Graduating instruments with a beam compass and simple scales was very hard. A simple instrument might take a week to graduate and then be filled with errors after all was done. With increased shipping, there was tremendous pressure for more and better instruments. At this time, in the latter half of the 18th century, Jesse Ramsden finished his graduating engine. This machine made it possible to accurately graduate a sextant in a half hour. This was revolutionary for ship navigation. The error at each mark adds to the error of all the previous marks, so the engine can be proven accurate by seeing what happens when the machine goes full circle. The last mark should exactly match the first. The graduating engine also made for more accurate devices in all fields. Greenwich-Paris. At this time, Cassini, director of the Paris Observatory, suggested surveying the precise distance from the Greenwich Observatory to the one in Paris. In England, General William Roy engaged Ramsden to build instruments, resulting in a theodolite and measuring rods with modern accuracy. The French surveyors also had the best instruments, made mostly in the French workshops of Nicolas Fortin and Etienne Lenoir. The survey established an accurate distance for astronomers and resulted in accurate maps of England. The Great Survey of India. Although there were other surveys of note, the only one I will mention here is the Great Survey of India. The survey, started by William Lambton, continued by George Everest and several others, began in 1802 and ended in 1871. The survey was done by connecting baselines to triangles. One thing to note is the use of triangle sets, in which the first triangle is connected to the last. The last point measured is also the first point measured. The total error in the set of measurements is the error in measuring the first point the second time. This works just as it did with the error in the graduating engine. This video started in the cold of the Arctic, measuring a baseline over a frozen river. Here at the end is a picture measuring a baseline in the heat of Calcutta. The romance of it, hundreds of porters and elephants marching through India, building towers, climbing hills and mountains, doing God's work among the population. The reality: heat, terrible food, dangerous animals, exhaustion, thousands of boring measurements and boring calculations in mind-numbing temperatures. At least I think they had gin to drink.